Dear ladies and gentlemen, it's my pleasure to introduce the multibody system package Exudyn in the next few minutes. I start with my contents. After short motivation, I will first introduce the simulation environment and then show the solver structure with a specific focus on the parallelization evaluated with test examples. Starting with the motivation, so our typical multiple systems, they're all here solved in our new simulation environment. They often have just a few bodies, like 2 bodies, 4 bodies, 5 bodies, 4 bodies in the first row. Some of them have a little bit more bodies, but might contain very different flexible components like many beam elements, a floating frame of reference formulation, or in the end really densely coupled kinematic structures or particles. Except for the particles, in fact, the number of bodies is sometimes very low, and conventional parallelization approaches are almost not to be applied, especially as they would need a huge number of bodies, as we see here on the right hand side. So before coming to the parallelization, I start with the simulation environment itself. Some key facts developed since the previous 3 to 4 years. The abbreviation is from Flexible Multibody Dynamics. It's a Python package with a C++ backend, which is really efficient, many time steps per second, but can also be used for large-scale systems, of course with much less time steps. The Python interface or even the environment is used to create models, add user functions, objects, perform some really high-level parameter variation or optimization, and it is in fact not only embedded into Python, but it's built around Python. Even providing Python modules that are purely written in Python to initialize rigid bodies, inertia, finite element importing, robotics, up to artificial intelligence. The 3D visualization allows you to adjust some settings and get the visualization as seen in the previous page. And there's a lot of documentation and reference manual which is directly linked to the code and being always up to date due to automatic code generation and documentation generation. To get it more detailed through, just visit our GitHub page, which can also be found in the paper. Some multibody related facts. It's a redundant multibody formalism with bodies and constraints that leads to differential algebraic equations. It's very useful for mixed, rigid and flexible bodies. It also includes a kinematic tree that allows minimum coordinate formulations, which can be used to efficiently treat robots and can be used with explicit integration. Some solver structures are shown here on the right hand side, but in more detail in the documentation. We have therefore implicit time integration like index 2 trapezoidal rule, index 3 generalized alpha, and we can also use explicit time integration. Everything independently of what kind of solution you want to do, also for static computation, we operate on a system data, which is then used in the system to compute mass matrix, right hand side, assemble some load vectors, and it operates on items, and these items are just simple 5 lists of nodes that provide the coordinates, objects that provide the equations, markers are then the interfaces between objects, nodes, loads and joints, and in the end we can apply loads and attach sensors. Just to say that the objects are very specific and are distinguished into bodies that have mass or connectors and joints that can be attached to markers. This very simple structure can then, of course, be computed quite efficiently, but the question is how to parallelize this, especially on a GPU. We have no solution for that yet. We have 85 total components like nodes, objects, markers, and we would need to hand code parallelization for that, which is kind of out of sight. Especially we also have flexible bodies that are still quite difficult and different. So that means that we have modally reduced bodies like here on the left, or we have real nonlinear finite elements. The parallelization that we use is based on a so-called task manager, which is similar to what you have also in Windows, but it's a very specific one used from the finite element tool ngSolve, which is also open source and developed in Vienna. There, standard threads parallelization is used, where at the beginning of every time-consuming job, a bunch of threads is started, which waits for the tasks, and the parallelization is then done in for loops, which are used like to compute the mass matrix over the residual. And the advantage of this approach is that the communication, exceptions, everything is made with very little overhead. We can or we can adjust this. Everything can be modified. It's based on templates. There's only just one disadvantage, that the extension to GPU is nearly impossible, and MPI is at least hard to do. Why don't we use OpenMP? Well, there's a large overhead when starting threads, and putting this framework, even with advanced and newer versions, into such a large code seemed to be unfeasible. Now we evaluate our parallelization with examples, and for that we use two different versions of this task manager. The original one with load distribution, as developed in ngSolve by Joachim Schöberl. And then there's a specialized version, we call it tiny threading with less overhead. It then has only 3.5 microseconds overhead per loop, which are still 1000 clock cycles of the CPU. But this is faster than the original version, and comparing this to starting threads in OpenMP, it is still 100 times or even 1000 times faster. Only limitation is the access to main memory. If we don't fit our models into cache anymore, then it becomes slow. The basic framework is shown here, where we have a serial code which has a for loop on some bodies. We compute the residual here, and if we compute the same with a parallel loop, it is almost having the same interface with some or with some lambda function interface, and we just need to take care to assemble all the thread, all the vectors that computed in one thread need to be assembled in the system vector in the end. The test environment is our 14-core i9 CPU, which is quite performant. We're using Windows, Microsoft Visual Studio. Just to mention that the Linux version is usually even faster. We use Python 3.8. And I have a couple of test examples, more details in the paper. We start with 1D masses, just to see the case of one mass up to 10,000 masses, where one mass has a large overhead from the system, so just the pure time integration takes a lot of overhead. And we see, due to this very optimized approach, we see in this tiny threading on the left, we see that we get a break even at around 30 mass points, where the parallelization is then faster, leading to less CPU time for the increasing number of masses. This is on a logarithmic scale, by the way, so that means that we have a maximum speedup of 4.9. In the original threading approach, it's a little bit less performant for smaller number of masses, but for larger ones, it's even better. This uses implicit time integration in this case, and just to mention that the examples show cases where the factorization is less important, because factorization of the masses of the matrices is still not parallelized in this case. Just the time-consuming right-hand side and mass assemblation and the typical multibody functions are parallelized here. The second example is a robot factory. It is a set out of 1 to up to 500 serial robots. They are modeled with the redundant formulation, having 42 unknowns then per robot, with 36 constraints using Euler parameters, with an implicit solver and 1000 steps to be computed. The same is performed for a minimum coordinate formulation of the same case, which is shown in the paper. For the redundant coordinates, we see remarkably at already 2 robots, which are then 12 rigid bodies, we get a speed up due to parallelization, and the overall speed up then of 2.5, a little bit less because limitations are due to the matrix factorizations appear here. And a similar performance also for the original ngSolve multi-threading approach. Now coming to the flexible multibody system, so we have here a belt drive with 480 beam elements, something that could be very typical, 1000 implicit steps, contact iterations, even the contact is here parallelized, and it's even a almost simpler case. We get a speed up of 3.3 for 10 cores, and this works really out of the box, no hand tuning. It is just a serial example that has then turned on the parallelization. The same also for this 18 piston engine with the floating frame of reference formulation and modal reduction to 550 unknowns out of the original 300,000 unknowns. Again here, out of the box, without any adaptations, we get a speed up factor close to 4 for this quite a typical multibody example. So coming to the conclusions, so for moderately large multiple systems, there's currently no parallelization method available, or almost no. Some companies are working on that, but in research we don't find really very much. Especially for general purpose systems, there is almost no approach. Of course, you can parallelize always certain like rigid body systems or special finite elements. Also in the implicit time integration for small scale systems, it's hard to parallelize because starting up the parallel solver is too slow. Still, GPU computing is out of sight for such systems, and also we don't have any approaches for that. But we can say that with our approach, we have a speed up of 3 to 4, typically for 10 cores, just with the bottleneck that the factorization is serially done in Exudyn up to now. With that already I conclude the talk, and I would like to thank you for your attention.